Welcome back to ECE 441A, 541A. Homework 6, if you're looking, is not yet posted, but it will be available, I hope today. But you really maybe don't have the information unless you've been reading ahead, which I hope you have been. But that will be covering Chapter 7. That's due a week from Friday, which, do you remember what else is happening on the 7th of November? Engineer's breakfast, and so there's no class that day, but your homework assignment, homework number 6, is due, and you can turn that in remotely or physically into a mailbox near you. But make sure the address is correct in terms of the box you submitted into. Exam number 3, just so you're planning your schedules or your calendar, that is in a few weeks, but it's the 21st. I think that's the Friday before Thanksgiving. So it's not in Thanksgiving week, but it is getting close. Lab number 2 is due this Friday, and hopefully you can get in to do lab number 2. Hopefully everybody hasn't waited until the last minute to perform lab number 2, but it's due this Friday. Today what I want to focus on is placing a generic characteristic equation into the standard root locus form, as far as get it in the representation that we want so that we can sketch the root locus. And we are going to be then dealing with the root locus diagram, which is Chapter 7. How do you sketch that? And if you are reading ahead, if you're flipping through and saying, what am I coming up to? You might look at table 9.6. Obviously, that's not in Chapter 7. That's in Chapter 9. But it now catalogs or displays these different ways of representing information about a system. They'll give you the loop gain, which think of the transfer function that includes the system, the controller, and the, let's say, the sensor dynamics. So it could be G sub C, G, H, that product. That's your loop gain. Then there's a polar plot, which is really just sketch that waveform as a function of the complex frequency variable S. Here it is for a couple of different, and you have to have good eyes to see this, but here are a couple of lines in table 9.6, and you can see that reading across the row, you're presented with different ways of explaining or providing information about that system. In row number 1, it's a first order system. It has a time constant given by tau sub 1. We have one pole. And you should be able to quickly think about what its Bode plot looks like. And that's in the third column of that table. It's flat, and then it reaches the pole, and then it starts rolling off at 20 dB per decade. And the phase starts at 0 degrees, which is in blue, and then transitions to minus 90 degrees. And that transition interval is 2 decades wide, centered around the break frequency. And that's your pole location. Then there's a Nichols diagram, but what we are talking about now in today and subsequent classes is this root locus sketch, which provides us a diagram, a locus of points that the closed loop poles possess when we increase the gain K from 0 up to infinity. We start at the open loop pole, which in this case is we just have one, and as we crank up the gain K, we drive that pole in the closed loop to more and more negative values, or it becomes faster responding in terms of our system behavior. That's for a simple first order. That's the first row of the table. The second row is a 2-pole system. The third row is a 3-pole system. The fourth row is a pure integrator, etc., etc. And you can look at that. If you have questions, you can say, there's the answer in the back. Table 9.6 will give you some indication as to what you might expect when you are trying to sketch these root locus diagrams yourself. That's just a heads up, and it's okay to read ahead or look ahead when you're reading a textbook. You can go into the subsequent or the later chapters and figure out where am I headed. That's allowed. I think growing up when I was first reading, I thought I have to start at page 1, read page 2, read page, and go all the way up linearly, but you can skip around and see where you're headed, which is, in this case, looking at table 9.6 for the answers, or where are we headed. We are going to then be studying systems in this standard block diagram. Let me just say this is sort of the standard block diagram where I have now isolated the gain in this forward path. I've combined, if I needed to, the controller and the plant into one forward transfer function, g of s. And if I have any feedback dynamics, any filtering, any processing of the output signal, that's indicated by h of s. This is in the standard configuration, and we should all know, once we've put it into this form, what our closed loop transfer function is. T of s. That's g over, well, in this case, kg, since we're factoring out the k. To explicitly keep track of that, we have kg over 1 plus kgh. That's the closed loop transfer function. What we are interested in, obviously, is the behavior of that system, and in particular right now, the transient behavior, and that's governed by the closed loop poles. In this particular closed loop transfer function, what determines or what gives us or provides us with the closed loop poles? What piece of this transfer function? And this is really a ratio of ratios, isn't it? G of s is a transfer function. That's a numerator over a denominator. That's all over another rational expression. So this really has sort of 4 parts to it if you wanted to think about it, but it's now your forward loop, kg over 1 plus kgh. The poles of that closed loop system are determined from the denominator expression. And that denominator expression is a rational expression, but the poles of the closed loop system are those values of s that cause that denominator to vanish. That's the definition of a pole. This is our closed loop transfer function, so the values of s that cause that denominator to vanish will be our closed loop poles, and we'll call this the characteristic equation. And if we don't set it equal to 0, we may call it the characteristic polynomial. The 1 plus kgh might be our characteristic polynomial. We set it equal to 0, and it becomes an equation. What we were seeing in table 9.6 was this movement of these values of s that cause that denominator to vanish. And those were indicated by blue lines with some arrows on them. That was telling us where our closed loop poles are migrating as we adjust this knob, this one knob that is k, our gain. We're now changing that knob k from 0 up to infinity. And we want to know, as we do that, how do these closed loop poles migrate in the complex S-plane? How do they move? That's the locus of points. It's the roots. It's our closed loop roots, and that's why it's called the root locus. We have this root locus, which provides us insight into where our closed loop poles belong or live as we adjust this gain k. And we might find that those branches of the root locus start moving into desirable locations in the complex S-plane. You now know from your design specification work where you like to have poles located, or at least your dominant poles. From the settling time, from the percent overshoot, from the peak time. Those now determine desired locations in the complex S-plane. We want to then be able to put anything that we're given. We might end up with, after deriving the transfer function, we may end up with a denominator expression that has k sprinkled everywhere. We want to actually put it into this standard form. That's our objective for today. How do we now manipulate the characteristic equation such that we can write it with that k isolated, scaling a rational expression, a numerator polynomial over a denominator polynomial? 1 plus k n over d equaling 0. That's our objective. If we now look at that, if we're now trying to find the values of s that cause that to vanish, it gets a little bit ornery if we just leave it in that non-common denominator form. If we put it over a common denominator, what values of s cause this expression to vanish? Those are going to be the poles, the closed loop poles. What values of s cause this to vanish? What are we isolating on? Is that a vague question? What values of s will allow this equation to be satisfied? Yes. We want the numerator piece of this mess. That's what we're focusing on. We need the denominator plus k times the numerator. That's now just going to be one polynomial. That now makes it a little easier to think about. We now have this one polynomial. We want to change k, and if you wanted to, if somebody said, what's the root locus, you could cheat and plug in different values of k, find the roots of that polynomial, and that will give you your closed loop poles for a particular k. We're just parameterizing all values of the closed loop poles by k, and if you wanted to plug in k equal to 0.1, k equal to 0.5, k equal to 1, k equal to 2, and sketch the migration of those poles, that's the root locus. We're just going to try to come up with rules that will allow us to sketch those more quickly than you plugging that through manually on, let's say, your calculator. Let's do that. Let's now do the following. I don't know if you can find the characteristic equation, but it's in black in the middle. It's the s plus k factor times an s plus 3 factor plus an s plus 1 equal to 0. Let's assume that you have now found a closed loop transfer function, and that characteristic polynomial on the left is in the denominator. And you're going, this isn't the standard form. I want it in 1 plus k n of s over d of s equal to 0. Figure out how to make that happen now. So how can you convert that polynomial characteristic equation into this standard root locus form? Because that's what we're going to be using as we move forward. So now find the little n, find the little d, if you're starting with this polynomial that I've given. Written another way, manipulate this characteristic equation, delta S equal to 0, to yield this star structure. Because this is what you're going to have to do every time when you start solving a problem, if it's not already in the standard form. You'll be presented with a transfer function, and somebody's going to say, how do the closed loop poles vary as you manipulate this gain k? And the way that we are manipulating the gain k is by moving it from 0 up to infinity. Has everybody found an answer? How many have an answer? Okay. What did you get? Did everybody hear that? N of S was equal to 1. S plus 1. That's not what I got. S plus 3. How's that? N equal. So what I ended up with was 1 plus k times S plus 3 over S plus, or S times S plus 3 plus S plus 1. Am I reading my notes right? Where did that come from? That's now what I want from this original delta of S equal to 0. I'm guessing since you guys are all, or most of you are ECE majors, you developed an algorithm to do that, right? And then you just plugged in the algorithm? Or is there a procedure or a process? It's not too dramatic or an involved process to make this happen. You could just say, okay, what's the process? The first thing that you want to do is separate the polynomial into two pieces. One piece that doesn't involve k, and another piece with all the terms involving k. So you separate that polynomial, or you say, here's my process that I'm going to follow. The first thing I want to do is isolate the terms involving k. Meaning we had a polynomial that was s plus k times s plus 3. I have to go back and find my original, plus s plus 1 equal to 0. That's what we started with. What this first step says is we now can say, well, let me just multiply that first two pieces, and I have s times s plus 3, or distribute those factors, k s plus 3 plus s plus 1 equaling 0. And now if I'm actually trying to isolate pieces that involve k, I can say here's a piece, or there are my terms that all involve a k, and here are my pieces that don't involve k. Is that clear? So that's not too hard. And the next piece isn't very hard either. What am I trying to do? I'm trying to get a 1. And then everything else is going to be scaled by k. I can do that here by simply dividing everything by what I've highlighted in blue. If I divide everything by all of those pieces that are in blue, I'm going to have a 1 plus a k times some ratio of polynomials. That's my second step and the last step. 2 is now to divide through by the terms not multiplying k. Which means if I start with what I had before, I have an s times an s plus 3 plus a k, s plus 3 plus s plus 1 equaling 0. What if I divide by what's in blue, which is s plus 3 plus s plus 1? Then I have my result, because if I look at this piece right here, all of that in the dashed cloud is 1 taken together, and there's my 1 that I needed. Everything else that remains is the k times this ratio of polynomials, meaning I can now say that I have 1 plus k times s plus 3 over s times s plus 3 plus s plus 1 equaling 0. And there's what I wanted, isn't it? And I might want to eventually put all of this together. That's a second order. I started with 2 poles. I'm going to end up with 2 poles. Now my poles n of s, or d of s, as I've been referring to those, are governed by s squared plus 4s plus 1. And that could actually factor into an s plus 3.732 times s plus 0.268. So I have 2 real poles that I'm beginning with. I can now write that in a standard way. I can say I have 1 plus k times s plus 3. That factor I will generically just say those are my open loop zeros in this standard form, and my open loop poles are given by the values of s that cause these 2 factors in the denominator to vanish. In this standard form, I may call this then the open loop zero factors. In general, I'll have more than 1 0. And the denominator, the d of s in our standard form, I will refer to that as the open loop pole factors. In the discussions then, when we're talking about a root locus and sketching the root locus, I will generically put whatever I start with into this structure, and then at that point forward I'll say, oh, what were our open loop zero factors, or where were our open loop zeros, where were our open loop poles, and now let's move on. Now we can start to sketch these poles and zeros in the complex S-plane. All of them were real. The 0 was at -3. And the 0 we indicate with an open circle. One of the poles was at -3.7. And another pole was at -2.68. What we're going to learn after we learn some rules is where do these poles, these open loop poles, at 0.268 and -3.7, where do they migrate as we crank up this gain k from 0 to infinity? In this particular case, it's fairly easy. This pole is going to approach that finite 0, and this pole as I crank up the gain, k, all the way to infinity, is going to march off to minus infinity. And the blue lines are what we will sketch. I'm sorry, the blue lines. The red lines are what we will sketch as the root locus. And we want to be able to do that for many different pole zero patterns. Let's look at another example. Are there questions on how we found this, before we move on, from our original characteristic equation? That's fairly straightforward. And that's all you're going to have to do initially, is put some characteristic equation, some delta of s that's in the denominator of your closed loop transfer function, which might be like this red delta of s, into the standard form, which in this case looked like that. Let's now look at another example. And now somebody might ask, how are the closed loop poles affected by adjusting k in the following system? Suppose for whatever reason, maybe you walk in the first day of work and somebody says, here is the system we've been playing with, and we need you to help us figure out what's going on. There's a forward block, and they give you this transfer function. Then they've added on to that a pure integrator. Here is your output y of s. Here's your reference input r of s. And then they say, well, we wanted to put in our gain here that we are adjusting. We're summing those two up and then feeding all of that back to compare with our reference input. And you go, that's not the standard diagram. Can you find the closed loop system? This is exam number 2 or exam number 1. Find the closed loop system for this. Give me a T of S for this system. Go. Your closed loop system is between the reference input R and the output Y. And you can work together if you want, unlike the exam. What did we come up with? Did we get an answer? Yes? So you've already put it into standard form. Oh, okay, so 1 over, is that what you said? One plus k? Maybe not. How did we, here, let me see if I can write this down. Did anyone get that? And if you wanted to think about this, if you were using Mason's gain, how many paths did you have? Just one, didn't you? You just had that path from input to output. That path is then the product of those two forward gains. So if you were doing this by Mason's gain, you would say path 1 is now 1 over s times s plus whatever it was, 1 s plus 2. How many loops do you have? You just have 2 loops, don't you? You have this loop, and you have that loop. And then it's just a function of creating your determinant and your cofactors. You have loop 1, depending on how you've defined loop 1. Loop 1, you could say, is this minus k over s plus 1, s plus 2. That's the first loop that I've indicated in blue. The second loop doesn't involve a k, and it only has 1 in the numerator. So loop 2 is minus 1 over s times s plus 1, s plus 2. Then if you use delta is equal to 1 minus the sum of the loops, and those loops both touch, so you don't have to go on, and delta 1, if you remove that path, you disconnect all the other loops, and there you have it. Now your transfer function, t, is p1 delta 1 over delta. Now, we have our transfer function, so that gave us this transfer function, t of s, which was 1 over s times s plus 1, s plus 2, plus ks plus 1. And let's say that's now this ratio of polynomials, where our polynomial delta of s gives us our characteristic equation. Which is our denominator, delta of s, equaling s times s plus 1, s plus 2, plus ks plus 1. And now we can put that into a standard form. That's not the original transfer function, obviously wasn't in the standard form, and we could have guessed that by the structure of our block diagram. That k was not sitting out in front. We didn't have nice paths in front. We had some k going in a weird way. We didn't anticipate having the standard form directly, but now what is the standard form for this? It's not too hard to generate, is it? In this case, the one term involving k is already isolated. We simply divide that piece by everything else. And this is now our standard root locus form. Is that clear? How that arises or where that came from? And what we need to do now is figure out our open loop zeros and our open loop poles. And then we can start sketching our root locus. Our open loop zero is when the numerator is set equal to 0 and finding the values of s that cause that to vanish, and that's pretty easy. We have 1, 0, and it's at the origin. What about our open loop poles? They're given by the values of s that cause that denominator, d of s, to vanish. Or that's now s times s squared plus 3s plus 2 plus 1. Or we now have a cubic, s cubed plus 3s squared plus 2s plus 1 equaling 0. And now, did you find in earlier classes how to find the roots of a polynomial? 310, 330, did you do that? Did you do a polynomial root finder in 330? I thought I heard somebody saying they were doing root finding. Where are your roots here? Maybe. Just as s gets really, really big, positive, what's happening to that left-hand side? If I really increase s, what's going to happen to the left-hand side? Just if I looked at delta of s here, and I said, let s march off to infinity, what's going to happen? It's going to get big, isn't it? What if I let s go to minus infinity? It's going to get really negative, isn't it? So I'm going between a big and a small, from s equal minus infinity to s equal plus. I'm looking for 3 values where that vanishes. I've now found that if I plotted this delta of s, maybe I'm going to really mess this up because this isn't what we're doing. This isn't a root locus. This is just finding the roots of that to find the poles, the open loop poles. But I'm starting there, and I'm finishing here. And what I don't know is whether this does this, or whether it does, that was convenient, something like that. I don't know whether it has 3 intersections of s or 1. But you can find that. You can find the roots of that on your calculator, can't you? What are they? Well, if you find the roots of that, you will find that, in fact, 1 is at minus 2.3, and the other 2 are actually complex, which means I have more like this picture. I only have 1 intersection of that delta of s with the, as I let s go from minus infinity to plus infinity. My second roots are at minus 0.34 plus and minus j 0.56. Those are my, what I'm calling the open loop poles. Now I can begin my root locus. Because I have my open loop zeros and I have my open loop poles, I can put down my x's and o's in the complex s-plane. If I begin a root locus sketch, all I'm doing to begin is sketching the s-plane, which is the real line and the imaginary line. That's my complex s-plane. And I put down my zeros, In this case, I had 1, 0, and I indicate that with an open circle. And then I put down my 3 poles. One pole is at minus 2.3. The other 2 poles are complex conjugates. I go a third of the distance towards minus 1, and then I go up about halfway. There's the beginning of my root locus diagram. So if you want 1 point on exam number 3, you would do this, depending on where we started. If I gave you that standard form, this might be worth a half a point. If you were starting with some transfer function, I'm going to have to start taking off more points, is what I'm saying. We're scoring very well on the exams, which is good. Now, what we have to do on exam 3 is figure out how do we sketch the root locus behavior. And in this case, depending on no analysis, it could be doing several different things. It could, we will learn, well, that this pole is going to want to go towards the right. We're going to develop these rules, but this guy's going to go to the right. What we don't know is whether he goes all the way to the right on his own, and these two just do something like this, and they disappear. They go off to infinity. Or maybe starting with the same pattern, maybe this guy starts to come in, and you know, these other 2 poles say, oh, I kind of like that guy that was at minus 2.3, and they start coming towards him. And they come in and they meet up, and then one goes off towards that 0, another one comes over and says hello to the other pole, and now these 2 go off this way. And depending on the relative spacing of these poles and zeros, we could have this top picture or we could have this bottom picture. And what we have to figure out is which picture do we have? Because on one solution, it'll be 0 points, and the other solution will be 20 points. And you're wanting the 20 points. So you're going to have to figure out how do we go, or how do we decide whether we have this picture on the top or this picture on the bottom. And how is that going to happen? We are going to develop rules so that you can figure out what's going on, and the rules will all be based on this standard root locus form. That standard form has this structure that's 1 plus k, let's say g of s, h of s equaling 0. That's the standard form. And we want to know what values of s cause that to vanish. And all of our rules are going to be based on this expression. But we can rewrite that. This is just on the left. This is something that's a function of a complex variable s. And what's a complex variable? It has a real part and an imaginary part. So we could think either rectangularly, or maybe we could think polar. We could rewrite this as k g of s h of s equaling minus 1. Just subtracting 1 from both sides. But minus 1, we can write differently, can't we? We can write minus 1 in polar form as a magnitude of 1 at an angle of minus 180 degrees, or any multiple thereof to give us minus 180. What we are going to do then is we're going to derive rules that provide us with ways of figuring out what values of s satisfy this relationship. If we plug in an s, when is the magnitude going to equal 1 in that left-hand side? And its phase is always going to equal minus 180. We'll pick up with rules on Wednesday.